This is the Spycraft 101 podcast. Welcome to your clandestine classroom. This is episode number 204 of the Spycraft 101 podcast. I'm joined today by Dr. Frank Close. Frank is Professor Emeritus of Theoretical Physics and Fellow Emeritus at Exeter College at the University of Oxford. He was formerly the head of the Theoretical Physics Division at the Ruthford Appleton Laboratory, Vice President of the British Science Association, and Head of Communications and Public Understanding at CERN. He is a Fellow of the Royal Society and won their Michael Faraday Medal for Excellence in Science Communication in 2013. He received the Order of the British Empire for services to research and the public understanding of science in 2000. You may remember Frank from episode 195 of this podcast when we discussed the atomic scientist Bruno Pontecorvo. I invited Frank back onto the podcast again to discuss his newest book, Destroyer of Worlds, The Deep History of the Nuclear Age, which is available now. It's a complete history of atomic research and its weaponization, plus the spies who worked to steal this research for the benefit of their own governments. By the way, if you're looking for a way to get friends and family as interested in history as you are, or if you want to learn something new and unexpected every month, then make sure to check out History by Mail. Every month, History by Mail will send you reproductions of famous and influential historical documents from American history. Accompanying the documents themselves are articles which put them in the context of their times and help you understand the impact they had on the course of American life. Topics are widely varied, so you're always learning something new across themes that include historic inventions, American wars, and foreign diplomatic relations. I'm really enjoying my own subscription because it's opened my eyes to historic events I knew nothing about. You can subscribe for yourself or gift a subscription at historybymail.com for as little as $6.50 a month. Just click the link in the show notes of this episode and use the discount code JUSTIN10 for a permanent 10% off your subscription. Frank, thank you for coming back.
Thank you.
Of course, after reading Destroyer of Worlds, which I just very recently finished, I was astonished to realize how little I really understood about nuclear physics and how much it has shaped the modern world, honestly.
Yep, it certainly has. And I suppose this year being the 80th anniversary of the birth of the atomic age makes it sort of special, and everybody's associating it with what happened in the Second World War and the bombs and so forth. But I'm sure, as we'll discuss, there's much more to nuclear physics and the way it's used than just weapons, thankfully.
Yes, absolutely. And that was what I liked the most about your book, because there are, to me anyway, this was my introduction to nuclear physics, really in a way that, is separate from just the Manhattan Project and the atomic spies, although, of course, that's a major focal point of the book as well.
Sure.
And you mentioned the 80th anniversary, but I was very surprised as well to learn that nuclear physics research really goes back much further than that. I think your book kind of starts off in 1895, doesn't it?
That's right, yes. I mean, it was 1895, cusp of 1895, 1896, when, by accident, Henri Becquerel, a scientist working in Paris, discovered that uranium, which is the heaviest naturally occurring element that we have here on Earth, it's very common in rocks, is emitting energy spontaneously without any prior stimulus. And we now know that this is energy that is contained within the nucleus of uranium atoms and has been there for 4.5 billion years, since the days that the Earth was formed, and has been emitting this energy all that time, very, very slowly. So that was the accidental discovery, which was almost missed. It was revealed as a little smudge on a photographic plate that Becquerel had kept in a darkened drawer and just developed to see what was there, and was astonished to discover this smudge. But it was so faint it was almost missed. And from that, today, we have developed nuclear power, the atomic bomb in the Second World War, and even now, even worse things, hydrogen bombs capable in principle of destroying all life on Earth. So for me, the fascinating story was, how did you get from that almost accidental discovery in 1896 through to where we are in the present day? Just in about 70 years it took to get from that start to the ability to build hydrogen bombs, and just 50 odd years to build the atomic bomb that started the atomic age.
Mm-hmm. Yeah, it was really astonishing, the inauspicious beginnings, I guess you could say, of that. But as your book clearly demonstrates, some of the best minds and the best intelligences in the world all work together to bring us to where we are now.
Yes, it was a sort of collective detective story. I mean, I imagined it being like a mystery that suppose you have got this one clue, this little smudge in a photographic plate. What do you do with it? I mean, how do you start? What's the first questions you ask? How do you go about doing experiments to move the investigation onwards? That is, of course, the fascinating story that we're going to talk about.
Yes, absolutely. So I did want to ask right off the bat, I know that the Curies, I know that's a very well-known name for just about anybody. You also refer to this as the Curie-Joliettes. They had some of the most impactful and earliest, impact really on nuclear research. Can you talk about how they got started with their research and what they contributed over the years?
Sure. I mean, Marie Curie and her husband, Pierre Curie, they picked up this discovery that Becquerel had made. And what they showed was that this phenomenon, which we now call radioactivity, was not unique to uranium. And by 1901 or so, they had discovered completely new elements that had never been seen before. Polonium, which was named after Poland, the country that Marie Curie came from. She was working with her husband Pierre in France. And then radium, which was so active that it glows in the dark. So they had shown that radioactivity is a phenomenon, a natural phenomenon. It's not something special to uranium. So they hadn't really told us very much about what it actually is, other than that it's something very impressive, because radium glowing in the dark was really quite something. And if you hold a bit of radium, you could feel the warmth. So that was the first real clue that this is something general. And I mentioned the fact that radium glows in the dark and it's warm if you hold it. They didn't realize then, but we now know that this radiation, if you're not careful, it's not just warm when you're touching it, but it can cause damage and indeed affect your DNA and generate cancers and so forth. Marie Curie, her husband was killed in an accident in 1906, but his hands were already suffering from the effect of handling this stuff. By the time Marie Curie died, in about 40 years later, she was so contaminated by the radiation that she and her husband, they were buried in lead-lined coffins in the Pantheon in Paris. These things we all understand now. It wasn't really understood back then, the hazards of these things. Pierre and Marie Curie, they had a daughter called Irene Curie, who, in my opinion, is perhaps the most significant of the female scientists in this story. Everybody's heard of Marie Curie because she discovered radioactivity and was very instrumental in using this radiation eventually to help cure people. But her daughter is the one who, in the 1930s, made what I think is one of the greatest discoveries, which we will come to in the course of the chat, I think.
What I did not realize until you just said it now, that radium was actually warm to the touch. And, that's tremendously ominous with the knowledge that we have now. To me, I immediately recognize the danger in that. But when did they actually realize that this, handling of radium and uranium could present these health risks? Was it decades later when things were too far gone for Marie and for Pierre and that sort of thing? Or was it much earlier?
Well, looking back with hindsight, remarkably slowly. I mean, the First World War happened, and there were these, what they call glow-in-the-dark watches, that radium's ability to glow in the dark encouraged people to start painting radium on the hands of the old analog watches that we used to use, so that you could see the time in the dark. And this was very common in America, that was developing, using uranium to make these improved products. And the way it was often done was to paint the radium on the very small hand. It was done by women who had little paintbrushes. And they would dip the paintbrush in the radium sample, paint it on the leg. And then, of course, what happens? They put the brush in their mouth and lick it to keep it sort of fine. They developed what was called radium jaw, which was a horrible condition and led to people dying. So certainly by the 1920s, it was very clear that radiation, if you are not careful, is very damaging. It is actually ironic, although I hadn't appreciated it when I was researching the book. Henry Becquerel, who was the first to discover radioactivity, very quickly realized that it could be used, perhaps, in order to attack things that you want to cure and so on. And so much of modern radiology can also be traced back to him, which might be a theme for another book someday, but I've already told you more than I know about that. But there's one other thing about radium. One often hears this thing that the Curies, and a man called Ernest Rutherford, who was a New Zealander who came across to Cambridge and then moved over to Canada, he really moved the story forward in 1905 and thereabouts. He discovered that there were two different forms of radioactivity, which he called alpha and beta. He began to make discoveries about the fact that when elements like uranium are emitting this radiation, they also change, that one element can change into another. And he was quite worried about this. He thought that everybody would think he was doing alchemy. You know, in hundreds of years ago, the idea that you could turn base metal into gold. Well, here for the first time, Rutherford had discovered it is indeed possible to turn one element into another through radioactivity. But he came across to Paris and visited the Curies. And there's a lovely story that was written up by his wife. You can imagine, it was a lovely summer's evening, completely clear sky in Paris in 1906, let's say it was. So in those days, there weren't many streetlights. In fact, probably weren't any at all. But it was very dark. And they went up onto the roof of the top of the apartment. And Pierre Curie very dramatically pulls from the pocket inside his coat a little glass bottle in which he's got some radium glowing. Rutherford's wife recorded that the glow was brighter than the Milky Way in the sky.
Oh, wow.
And it was bright enough that they could already see the damage that was being done to Pierre Curie's fingers. So by then, it was already obvious that this could be hazardous stuff, but it took some time before I think this is really fully appreciated.
Yeah, certainly. And that's terrible for the early pioneers. Of course, clearly they suffered a lot for their research, but in the end, I think in the long run, they saved, untold hundreds of thousands or perhaps millions of lives with this research, as we'll talk
absolutely.
about later.
I mean, to jump forward slightly to carry the story on, Enrico Fermi, who was probably one of the greatest experimental scientists of the early 20th century, during the 1930s, he did some very key experiments when he was still working in Rome. And these involved him inducing radioactivity in some elements. And then to do the measurements, they had to take the sample down a corridor to get it away from where all the radiation stuff was being done, so that if they measured radiation, they knew it was in the sample and not something that was still back in the lab. So he was running down the corridor, clutching these radioactive materials to his tummy. He died around the age of 52. So that shows that even by 1930s, it was not really appreciated widely, the danger of this stuff.
Yeah, that's horrifying. And to go back to the radium girls for a moment, I looked up a few photos of them, and it's some of the most gruesome stuff I can imagine. What an awful way to suffer and then die, of course. Just horrifying, really. So, Frank, since you mentioned Ruthford, I noticed that you were the head of the theoretical physics division at Ruthford Appleton Laboratory. I guess that's his namesake, isn't it?
That indeed it is. It was named the Rutherford Laboratory because it was a nuclear physics and particle physics laboratory that started back in the 1950s. And it was named after Rutherford as perhaps the greatest nuclear physicist, certainly in the UK, and one of the greatest in history.
Mm-hmm. I love your little anecdote at the beginning. I guess he was first accepted into his advanced studies program. He was farming potatoes, wasn't he, in New Zealand?
That's right. In fact, wonderful accidents in this business. Indeed, as you say, he was farming potatoes. He had been at university in New Zealand, and he had applied for a scholarship. There's a special scholarship that could take people across to the UK. It turns out that he came second. In fact, we now know there are only two people that applied for it, so he came last.
Wow.
One of the conditions of this scholarship was that it was supposed to be of great use to the economy, and the person who won it was a chemist who had some method for extracting gold from ores. Now, in New Zealand in the late 19th century, they were having their own sort of mini gold rush like you had in California some decades before. And so I can see why it was that this person who had a good way of extracting gold was deemed to be the person who was most worthy for the New Zealand scientific industrial future. It turned out, however, that this guy was already earning money, and the value of the scholarship would be less than the money he was already earning. And he wanted to get married and couldn't support a wife on the scholarship. So he turned the scholarship down.
Oh, wow.
And by that accident, Rutherford won the scholarship. Rutherford at that time had been working on radio waves. Radio had only been discovered about 10 years before that. And Rutherford, as a student, was doing work with radio waves, which was further ahead, we now know, than Marconi. So he came across to Cambridge wanting to work on radio at about the same time that these discoveries by Becquerel and so forth emerged. And the people at Cambridge realised that this was really the big key future, and so diverted Rutherford to work on that, in part because they also knew that researching on radio was going to be very expensive and they couldn't be sure to get the funding for it. So by these accidents, Rutherford becomes one of the greatest scientists in the elucidation of what an atom is made of, and Marconi becomes the guy who we all know for radio.
Wow, that's unbelievable. I did not realize that. Ahead of Marconi, and then he just decides to switch specialties and become the Ruthford of nuclear physics. That's incredible.
Absolutely, yes.
1 in a billion.
Yep.
Wow. So one thing actually, and not to skip too far ahead really about Ruthford, perhaps I'm reading a little bit too much into it, but you mentioned as he got older, and of course he was kind of the father of so much, but he apparently mentioned repeatedly that, he wanted to leave a lot of the work to the younger scientists and he was getting older and that sort of thing. And to me, that spoke to a kind of an amazing level of humility. Really, was that your take on him as well? I mean, not just a genius, but also sort of like a humble type of guy that was, happy to be part of like a larger group of contributors and scientists?
Well, Rutherford, when he started as a brilliant student, science was still being done by, an individual or maybe two people working together, using whatever they could cobble together, doing little experiments on a bench top, using bits and pieces that they found around the lab.
Mm-hmm.
Maybe a glass blower would blow a glass tube so they could pass gases through it. But it was a very small scale endeavour, and it was through that level of genius that Rutherford discovered, first of all, not just that atoms can change form, but deduced the structure of the atom. And it was he that discovered that the atom, if you like, is like a miniature solar system where the planets are like little electrons, particles called electrons, are whirling around like the planets on the outside. And then at the heart of this thing is what we call the atomic nucleus, if you like, the analogue of the sun. And the atomic nucleus is where most of the mass of an atom is contained. It's incredibly tiny and small, and it was Rutherford that deduced that. He was able to show that this energy of radioactivity was actually coming from the nucleus, though he didn't know how. So he basically taught us pretty much everything about the atom by 1920. And by this stage, he was now becoming, a senior person. He had won the Nobel Prize. He had been knighted, and in fact, I think was soon to enter the House of Lords, which is as far as you can get in the hierarchy of the establishment in the UK. And so now students were coming to work with him. And the nature of science itself was beginning to change in that by 1930, rather than one or two people doing a small experiment on a bench top, the experiments themselves were becoming bigger. And the teams of people, 4 or 5 people working together, and Rutherford now was running and overseeing the whole of the laboratory. So in that sense, it was his know-how and vision that, if you like, he could see over the horizon, and the new generation coming through with the energy and enthusiasm were being directed by him as to where to go. And it's in that sense, I and my generation have done our thing, and now it is for the next generation to build on this and follow it through with my guidance, obviously. But that's probably how it was.
Okay. I see. That's amazing. You talked a lot, Frank, about envisioning the structure of the atom and understanding it. Of course, at what point did people start to talk about or attempt to split the atom, and why would they want to do that? What did they foresee as the potential ramifications of that?
Well, Rutherford had discovered the nucleus at the heart of the atom. The nucleus is charged with positively charged electricity. Like charges repel and unlike charges attract is one of the mantras that we all know. Electrons are negative, the nucleus is positive, so it's those opposite charges that hold an atom together. But there's a great mystery about, well, what does the nucleus consist of? It's just a lump of positive charge. Well, Rutherford had deduced that as you move up the periodic table, hydrogen, the first element, has just got 1 positive charge in the nucleus. Helium has got 2, all the way up to uranium, Number 92 has got 92 charges. And so Rutherford had the insight that there must be a carrier of this charge, and he called it the proton. The proton is the basic particle that carries positive charge. One proton gives you the nucleus of hydrogen, two protons gives you the nucleus of helium, and so on. But it was also possible to measure the relative weights of different atoms. And this is where the first puzzle emerged around 1920, that the weight of helium is about 4 times that of hydrogen, even though there are only 2 protons in there. And uranium with 92 protons weighs in at about 240 times. So something extra was needed. And this extra obviously must give weight or mass to the atomic nucleus, but not change the electric charge. And so Rutherford postulated that there must be something which he called the neutral proton or the neutron. And this he postulated in 1920, but nobody was able to find it for about 10 or 12 years. And so this really was inspiring this whole question of, so what actually is a nucleus? How do these protons and neutrons work, assuming the neutron is there? Can we get inside a nucleus and see what it is made of? It was obvious that the nucleus must have a structure, but to find out how it was built, you've got to somehow get inside it. There were very powerful forces holding it together, because if you've got 92 positive charges in a nucleus of uranium, and like charges repel, there's a huge electrical force trying to blow the thing apart. So there must be some very powerful glue holding it all together. And so that's what led to the beginnings of what were called atom smashes, ways of speeding up protons in particular. Hydrogen was easy to strip the electrons off the atoms and produce a beam of protons, which you would speed up by applying electrical forces to them, giving them electrical kicks. And they would then blast into atoms of lithium or other elements and see what happened. And what happened was that the nuclei of these atoms were blown apart into pieces, hence the atom smashing. And from this, they were able to put the pieces together metaphorically to deduce what a nucleus really consists of. And by 1932, the idea was that the nuclei of all atoms are made of protons and neutrons. Different atoms have different amounts of stability depending upon how these neutrons and protons are arranged. And it was the discovery in 1932 of the neutron in an experiment that actually proved that this picture was right. And so 1932 is often regarded as the key year when nuclear physics came of age. It had taken 30 years from the discovery of radioactivity to deduce that radioactivity is coming from inside the atomic nucleus, that the atomic nucleus consists of protons and neutrons, but how these protons and neutrons are actually assembled to make these nuclei, and why it is that some nuclei emit radioactivity and other ones don't do at all, that was still for the future. But the tantalizing promise, if you like, or the tantalizing puzzle was this. I mentioned how radium glows in the dark. And back in 1905, Rutherford had measured the amount of energy that radium is emitting and realized that it had been emitting this for as long as the Earth had existed. And so there was a vast amount of energy inside it. And this gave rise to a thing we often read, which says that the amount of energy contained in a kilogram of radium would be enough to drive a ship across the Atlantic from London to New York. And that is indeed true if you're prepared to take 100 years over the trip. And the problem is this, it's sort of obvious once I say it, if radium and atoms have been emitting this radiation for 4,500 million years, it's obviously coming out very, very slowly. So slowly that there was nothing very obvious you could do with it. And the question was, how can we speed it up? How can we usefully get energy out of the atomic nucleus? And even as late as 1933, Rutherford famously was saying that anybody who thinks you can extract useful energy from the atomic nucleus is talking moonshine. So that shows that even genii don't always see the future.
Right, that was fascinating. Actually, the book is candid in some ways that there were a number of missteps and incorrect assumptions, or incorrect theories and that sort of thing along the way. Even among the smartest people in the world, it was not like a steady and even path towards where we are these days. But yeah, sometimes people just went the wrong way, really,
That
and sometimes
yeah,
took years to correct.
that's absolutely true. I mean, that people's understanding of science is formed by the winners telling the story with hindsight and giving the impression that it was a sort of you got from A to Z in a straight line. Actual fact, much of the time is taking wrong turns, making mistakes, learning from your mistakes, improving the experiment, moving forward or sideways, and comparing notes. So it's a very gradual process,
Hmm.
backwards and forwards, sideways, and occasionally you make a bit of progress.
Hmm. Absolutely. So, since you mentioned the fast liberation of energy, was that as envisioned not just as an energy source, but as a weapon? I mean, like how quickly did it occur that this might be like an explosive release of energy and not just like a steady stream?
Oh, that's sort of quite slow. Well, yes and no. H.G. Wells, the famous science fiction author, he wrote a book called The World Set Free back in 1910s, 1920 probably. And this was inspired in part by the discovery that there was this vast amount of energy trapped inside the atom. And, there had been speculation that if there was some way of extracting this energy faster, the possibility of, well, one beautiful phrase was making the deserts bloom, using this energy to be able to create wonderful things and so forth, or possibly, if the wrong people got hold of it, to make a weapon of unimaginable power. And H.G. Wells, it was he that in this book coined the phrase atomic bomb.
Oh, wow.
But that was fiction. And this was the point. I mean, the fiction made a big impact on people.
Hmm.
And in part, that was the reason why Rutherford by 1933 is saying anybody who thinks you can get the energy out like this is talking moonshine. Because it's one thing to write science fiction, it's quite another thing to do science fact. That's the hard thing about it. Most of our ideas turn out not to be the way that nature does it, which is one of the really frustrating things. It's easier to write fiction than do factual research. So the idea was there in fiction, but there was no indication whatsoever that you would be able to extract this energy in a useful way. It wasn't until 1934 that Marie Curie's daughter, Irene, made the breakthrough that showed that it is possible to irradiate. After the neutron had been discovered, it was possible to irradiate elements of ordinary stable matter and make them radioactive. So, for the first time, here was a way of liberating some of the energy from inside the atom. Not enough to do anything dramatic with, but certainly enough to make great contributions to the world of medicine. So, for example, if anybody has ever had a PET scan as a diagnostic, you have been making use of what's called positron emitters, certain forms of atomic nuclei that are created in the laboratory by irradiating other forms of nuclei. And these particular forms emit what's called positrons, a form of antimatter. And this turns out to be key as a lifesaver to medical diagnostics. And also, these artificially induced radiation materials are used in radiology and medicine and industry and so forth. So that was 1934. That's the first hint, well, the first direct evidence that you can speed up the liberation of nuclear energy a bit, but it's the first step. But nobody is thinking at that stage of getting a weapon out of all of this. And actually, I conjecture, we can talk about this later on, that had the Second World War not intervened and the fear that the Nazis might get there before the rest of us that really made the impetus to develop the atomic bomb, it's possible the atomic bomb might have been, at the very least, significantly delayed because it was such a huge enterprise. But we're getting ahead of
Oh,
ourselves
yeah.
by chatting about that.
Yeah, yeah, of course. Yeah, that's a great point. Actually, I had not considered that, but you're right. That is for a few moments from now. So this research is going on throughout Europe. As you said, you've got Fermi and some of the other guys in Italy. You've got in Germany. You've got researchers in the United Kingdom. did this work become more difficult, like these collaborations and that sort of thing, as things slowly built towards the beginning of World War II, in the mid to late 1930s?
No, I mean, throughout the 1930s, nobody had the thought that there could, in practice, be a bomb or explosive release of any sort. That what had been achieved by 1934 was simply a means of getting some of that energy out fast enough to be of use to medicine and so on. The idea that there was a weapon there was certainly not on anybody's mind. The first clue that, well, there might be something that you could do comes in 1938 with the discovery of what is called nuclear fission. And that is the real story where the whole business about the bomb begins.
Okay, I see. So the national governments are not yet paying attention to these advances in nuclear research until around 1938, 1939, then? Is that correct?
That's true. In fact, one of the ironies we might touch on is that in 1940, after the war has begun in the UK, two Jewish emigres from Hitler had managed to escape to Britain. But because they were classed as enemy aliens, they were not allowed to work on the development of radar, which was the big hot development and the big secret at that time. But they were allowed to work on nuclear physics because that didn't have any apparent use.
Wow.
And those are the two people who we will see are what I would say the real fathers of the atomic bomb and not Robert Oppenheimer.
Okay, yeah, that was actually going to be one of my upcoming questions as well. So I know that a few of these scientists, to back up very briefly, like a lot of them, they had to put their work on hold during World War I. And I think some of them were doing working with X-rays, as I recall from the book. That was kind of the most, practical and immediate need during World War I was like the X-ray ambulances and that sort of thing. But other than that, all of this research was what they were just working privately, like through schools, private funds, that sort of thing. There was nothing else government related until 1939.
Well, certainly you mentioned X-rays, that in the First World War, yes, I mean, the ability of X-rays to cast shadows of broken bones was recognised almost overnight. That was the very start of this saga. And indeed, Marie Curie and her daughter during the First World War had these machines to generate X-rays so they could actually X-ray injured troops. So X-rays were certainly one of the key diagnostics by the First World War. During the war itself, of course, people pretty well stopped their research because some of them were in the army. Ernest Rutherford was consulted by the British government, and he was secretly working on developing what we now call sonar as a way of detecting submarines underwater.
Oh, wow.
But he did manage in his spare time to do a bit of research in the laboratory at the university, and that is how he discovered the atomic nucleus and so forth. If almost in his spare time, you might say.
My gosh. There's nothing he couldn't do, it seems like.
That's probably true.
Amazing stuff. So, since you mentioned Robert Oppenheimer a moment ago, what was the actual impetus for the national level bomb projects? I know about tube alloys in the UK and Manhattan Project in the US. I mean, did these begin because Germany had started theirs, or were they initiated just totally on their own? Like, what was the start of these actual weapons projects?
Well, what happened at the end of 1938 was the discovery of what's called nuclear fission, which was that when neutrons hit a lump of uranium, it's possible that the uranium nucleus can be split in two. And that is what's called fission. And it liberates 1,000,000 times more energy than had ever been liberated before. So this is the first time that a huge amount of energy can be liberated from a uranium nucleus. But it does more than that, because the nucleus of uranium contains a lot of neutrons and 92 protons, more neutrons, if you like, than it needs. So that when it's split in two, a couple of these neutrons sort of drop off and are there free for them, in their turn, to hit further atoms of uranium and repeat the fission process on them, liberating energy and in turn liberating two more neutrons each. And so the possibility of what's called a chain reaction, people realized that within about 1,000th of a second, you could have one neutron splits, produces two, splits, makes 4, 8, 16, 32, like that. Each of those liberating energy in a vast amount, potentially explosively. And so that, the end of 38, early 39, is the moment when, at least in theory, the possibility of liberating energy from the atomic nucleus explosively comes into consciousness. The Second World War in Europe starts in 1939. Uranium being key to this business means that research on uranium becomes classified secret. And in Britain, great advances are made, which I'll come back to in 1 second, because what I want to do is to make contact with the thing that most people listening to this will have seen, namely the movie Oppenheimer, because that's a great movie, but it's a great work of fiction as well. First of all, it gives the impression that the moment that fission was discovered, Oppenheimer had a diagram of a potential bomb on his blackboard in his office in Berkeley. Well, I mean, he may well have done, but it ain't as simple as that, because the great Danish theorist Niels Bohr said, just a second, I mean, if it's that easy to split uranium and make an explosion like this, why aren't the rocks of the Earth, which are full of uranium, exploding all the time? Mm-hmm. And the answer he provided was key to the whole business. It turns out there's two forms of uranium called uranium-235 and uranium-238. What these numbers are doesn't really need to concern us very much. It's the total number of neutrons and protons in them. But it turns out that 235 with an odd number is the magic one, if you like, that gets split and releases its energy. 238, you hit that and nothing much happens. So, well, that's the first part of it. Bohr said it's 235 that's doing the job, not just any old bit of uranium. Mm-hmm. The second thing is that he pointed out that if you take a lump of uranium from the rocks around us, uranium-235 is only about 7 in every 1,000 atoms. In other words, it's very rare. Mm-hmm. So a neutron might hit one of these 235s and split it in two, liberating some energy and 2 neutrons. But the chance that those neutrons find another of these rare 235 form to do the job again is very small in natural uranium. That's the reason why the rocks around us aren't exploding. That, incidentally, is the reason why at the present time there's so much concern about what's called enrichment of uranium. Mm-hmm. Meaning, if you take natural uranium, is there some way that you can increase the relative amount of the 235 to a level that the chances of the chain reaction continuing now become, likely? And that is what, of course, has been going on with the Iranians, who have been enriching uranium beyond levels that are needed just to liberate energy gradually, like in a nuclear reactor, but to the levels where you could liberate it explosively as in a weapon. But there we are in 1939. Bohr has pointed out normal uranium doesn't do very much for you at all. It's uranium-235 that you need. Now, that insight didn't seem to have made any impact at all in the United States. Leo Szilard, a Hungarian physicist who had migrated to the States, contacted Albert Einstein and induced Einstein to write a letter that went to President Roosevelt, alerting him to this discovery of nuclear fission and the possibility that this could make weapons, and that it was very important that one started looking into this, which is quite remarkable because Einstein, everybody has heard of him, everybody thinks of him as the greatest guru in physics. Well, that was indeed true in 1905. Mm-hmm. But by 1939, I mean, he was out of it. Discoveries had been made of which he was completely out in left field, as we say, but he had a great name. And so Szilard goes to him, gets him to sign this letter. It turns out that Einstein was totally unaware that nuclear fission had been discovered, let alone that Bohr had shown that this is not going to be very much use, given that uranium doesn't have the key U-235 in it very much. But nonetheless, this letter went to Roosevelt, and a project was started to start developing the work to make like nuclear reactors to get energy out of uranium. But for the next couple of years in the States, the thought was that you might be able to extract energy from uranium if you had a ton of the stuff, but there's no way you can make a weapon that explodes as a bomb if it's weighing a ton, So that's a complete red herring as to what actually happened. The American work was looking to get energy out of uranium. Meanwhile, back in the UK, these two Jewish emigres, Otto Frisch and Rudolf Piles, they took up Bohr's idea and they said, well, just a second, suppose somehow I was given a lump of uranium-235 where everything was 235, not just 7 in 1,000, but everything. How much would I need to make an explosion? And they did the calculation. This is 1940. They did the calculation and discovered that about the size of a grapefruit would be enough to be giving rise to an explosion equivalent to that of about 1,000 tons of dynamite, that it would emit radiation, that the blast would be so powerful that there would be no material way of defending yourself against it other than to have a weapon of your own. And the thing that worried them was, often what happens in science is that although you spend a lot of time going sideways and backwards, once you get to the answer, it suddenly becomes so obvious that you wonder why it took so long. And these two guys immediately panicked. They thought, surely Hitler's scientists have already seen this for themselves. Could it be that the Nazis are already designing and building such a weapon? We have to have one ourselves. And so it was Frisch and Piles in March 1940 who wrote this letter, which worked its way up to the British government, alerting them that you only need to get this small amount of uranium-235 to make this weapon, which could literally change the nature of warfare. And for once, that isn't hype. That is indeed how it turned out. Mm-hmm. So for the next, and this began a project in Britain, which was given the code name Tube Alloys. Conveniently meaningless, so that if any spy stumbled upon it, they would not take any notice of it.
Right.
So this project began, and for the next 18 months in Britain, a lot of work was done to work out how in practice could you enrich uranium, produce uranium-235, how much do you have to make, and so on. And Rudolf Piles was the leader of this project, and his assistant, it turns out, was the well-known Klaus Fuchs, who is best known as a spy. Fuchs started working with Piles very early in this project. Well, sorry, Piles had the idea in 1940. Piles and the others in the UK had been working at this for up to a year. But by 1941, the problems that had to be solved were so vast that he needed more help. And Klaus Fuchs, who was also deemed an enemy alien, he came from Germany. He wasn't Jewish. He had escaped from Germany because we now know he was a communist and the Gestapo were after him. Mm-hmm. He was a great scientist who Piles knew and worked with Piles. And by chance, he had been taken on by Piles just a few days before the pact between Stalin and Hitler, the non-aggression pact, broke down. And that night, the British Prime Minister Winston Churchill went on the radio and said, the Russians are now our friends and we will do everything possible to help them. And so you can imagine yourself as Klaus Fuchs in this situation, working on this top secret project, realizing that this could indeed change the nature of warfare. And your Prime Minister has just assured you that we will do everything we can to help the Russians, who have been frozen out of this project because we were suspicious of Stalin. I mean, he's our ally now, but he was an ally of Hitler last week. You can't really trust this guy.
Right.
But that's how Fuchs came into it. So this is 1941. Now, the US is not yet in the war. Pearl Harbor has not yet happened. But Britain is in desperate straits and very much wants politically for America to become involved on our side. And so Winston Churchill sends this delegation of scientists across to North America with a scientific dowry, basically showing the great advances that have been made in science and technology, such as radar and various other things, and effectively just giving them to US scientific technology in order to encourage the development in the United States of this military potential stuff, and by that get the US involved into the war. I mean, the Japanese, of course, completed that process without anybody needing to help it. But that was the thing. And it was only at that moment that in the United States did the knowledge get transferred to them, to you, that you only needed to make a kilogram of uranium-235 to make a weapon. And that is when the Manhattan Project began, the reason being that although this idea had been developed in the UK was still very much subject to bombing, the Blitz, and the project to develop such a weapon would be a vast industrial project. There would be no possibility of keeping that under wraps out of reach of German bombers. And that's the reason why the project took place in North America, and in particular in the United States. And a team of British scientists came across and worked, many of them at Los Alamos, including Klaus Fuchs, of course, with the huge efforts. So it was very much the United States taxpayer who paid for the construction of the atomic bomb, but the origins and the brainpower that stimulated it came from these two guys in the UK. And that's the reason why I say that the father or the fathers of the atomic bomb were actually Frisch and Piles, two, ironically, German Jewish emigres from Nazism, and that Oppenheimer was the midwife who led the project, the intellectual part of the project, and enabled this conception to be born, if you like.
Okay, I see. Yeah, I knew that his background was in quantum mechanics, quantum physics.
Yes.
Right? Not nuclear physics necessarily. So, I mean, clearly it ultimately led to a successful bomb, of course, but it was not his insights necessarily that created that.
No, that's absolutely true. But you made an important point about Oppenheimer. Oppenheimer was very good working in quantum mechanics, which had really itself only been born about 10 years before the war. And Oppenheimer, I think, probably almost brought knowledge of quantum mechanics over to North America. That is why he was, in theoretical physics, so influential. He was very much aware that quantum mechanics would be one of the key things to understanding the mechanisms that could generate energy from a nucleus, be it explosively or through nuclear power and so on. And I think also it was key, he hadn't won a Nobel Prize. He did work that was almost there, but nothing at all that you could put your finger on and say, that's the Nobel Prize. And I think that plays two key roles in the question of why was it Oppenheimer who became the person that General Groves, the overall runner of the Manhattan Project, chose. At one point, it was the fact that Oppenheimer did not have a Nobel Prize that attracted him to Groves, because Groves felt that these Nobel Prize winners, they were all hugely intellectual people who were outside, the lost contact with the real world, whereas Oppenheimer was somebody he could talk to and who he felt was somebody who did understand the real world, which indeed turned out to be true. The other thing from Oppenheimer's side of it, in my judgment, he had not won a Nobel Prize. He had done good work in quantum mechanics. He felt that he had not received all of the recognition that he deserved. And I'm sure when Groves comes to him and tells him about this project, Oppenheimer judges this could be his passport to immortality. And indeed it was.
Right. So him becoming known as the father of the bomb, was that in part because of self-promotion, you think, or was that like a media blitz afterwards that he was happy to take advantage of?
Well, I think it all happens in 1945, after the war has finished and General Groves really took control of PR. There was a thing called the Smith Report, which basically had everything you needed to know to build an atomic bomb in it, that was published in 1946 and was pretty well freely available. Remarkable. But Groves really controlled everything that went into that report. And there was not a mention of anything other than the American side of the story. The fact that there'd been any Brits or people from elsewhere was airbrushed out totally. And that became a bestseller. Groves later wrote his autobiography called Now It Can Be Told. And again, in there, the impression is that the whole thing was an American thing, which indeed, economically and politically, that was perhaps the right thing to do. After all, as I said, the American taxpayers were the people that paid for it, and so they had to be shown what a wonderful thing had come as a result of it. But the consequence of this is that the story came out that the bomb had been created in America, it had been led by, and Oppenheimer was the father of this, and so forth. This led to the Smith Report, which in turn is what led to, the book the book that inspired the Oppenheimer movie, I can't recall, but that is also very much based upon this Groves version of history.
Okay.
And so this is then fed through to the Oppenheimer movie, where you have the impression that the only thing that the Brits contributed was the spy, namely Klaus Fuchs. I mean, Rudolf Piles makes no appearance, nor do any other of the many people who were involved, not least in the early stages, but bringing the whole project through to completion in Los Alamos and elsewhere. But get your story in first, and then the rest of the world will play catch up trying to correct it, as we are discovering perhaps today in other contexts.
Wow. Incredible. Yeah, the narratives have to be put into place as soon as the fighting is done. That's pretty incredible. Unfortunate. Yeah, and you mentioned like Szilard, the Hungarian, and Teller, and Frisch and Perls, and Niels Bohr's, Fermi. I mean, so many European brilliant scientists, and then they take a backseat to Oppenheimer, who was not even a nuclear physics guy. That's tragic.
I mean, you mentioned Szilard and Fermi. I was just reading the letter, what's called the Einstein letter, that supposedly started the American involvement. This letter was actually written by Szilard, who went to Einstein and got Einstein to sign it and put his signature on it so that it carried the weight. But the first sentence of it refers to work by Fermi and Szilard has shown that various things are possible. Well, indeed, Fermi and Szilard had done experiments on the possibility of a chain reaction, and their work was inconclusive. But Szilard presented this as if it had all been solved, and Fermi, quite contrary, believed for a long time that the idea of building an atomic weapon was very, very unlikely. But, you don't see this sort of in the history. Szilard was a person who was always optimistic.
Wow. Okay. Yeah, what a tremendous collection of intellectuals it was. It really is amazing. And Frank, I want to ask a little bit about Fuchs' role in all of this. I believe he was working on the implosion device team, wasn't he? A number of teams gathered together. Was he like a critical part of the development, or was his main contribution just passing everything along to the Soviets throughout the whole project?
Well, he certainly did the latter.
Yeah.
But Fuchs actually was an important scientist in his own right. That Piles had wisely brought Fuchs, from the point of view of science, Piles had wisely brought Fuchs on board back in 1940. Fuchs was a very good mathematician. He's not an innovative scientist like Enrico Fermi or Rutherford or anything at all like that. He's very good at solving problems. He's not going to create new pathways of discovery, but he's very good at solving problems. And so he initially, in the days of the British involvement in 1940-41, was involved in working out the mathematics of how you would go about enriching uranium. And when the Brits first moved across to New York, they completed the design which led to the Oak Ridge National Laboratory in Tennessee, which is the place where the uranium that eventually formed the bomb for Hiroshima, where the uranium was enriched. And that was very much due to work that Fuchs and Piles and some others had done in and around New York. Then the whole project moved across to Los Alamos. Well, Los Alamos is where the bomb is constructed. Oak Ridge is where the uranium for the Hiroshima bomb is being enriched. And up in Washington State at Hanford, some nuclear reactors have been constructed which will breed plutonium. Now, plutonium is the fuel that made the Nagasaki bomb. Plutonium, just like Uranus, Neptune, Pluto in the solar system, uranium, neptunium, plutonium.
Oh, wow.
Plutonium is an element that doesn't exist naturally on Earth. It existed 4.5 billion years ago, but it's so radioactive it has all died away, leaving uranium as the heaviest that you tend to find around here. So to make plutonium, you have to create it by bombarding uranium in a nuclear reactor, not so much to make fission and liberate energy, but to add neutrons to the uranium nucleus gently, and then natural radioactivity will move it up, eventually forming plutonium, which the chemists can then remove one atom at a time until you've got enough to make a weapon and do tests with. So that's what was going on up in Hanford. And the insight that plutonium could be a better way to make an explosion had come in 1942 or so. And it was the realization that this could be the way to produce bombs, at least in future, but also for technical reasons was extremely difficult. Plutonium indeed is highly unstable, which is a good thing when it comes to making the explosion, supposing you can get the plutonium held together long enough to do it when you want it, rather than to do it prematurely and so forth. So this was the problem which became known as implosion, to bring individual pieces of plutonium together very rapidly to coalesce into a little ball which would then explode, to make a sphere of plutonium pieces which would then implode into this central mass and make the explosion. And working out how to do that, somebody said it was like having a glass full of beer and to drop a golf ball into a glass of beer without any of the froth coming over the edge. It's all but impossible.
Oh, wow.
But it was a mathematical problem which Fuchs and Piles and von Neumann were the three key people to solve. So Fuchs and Piles were 2/3 of the team who made the theoretical analysis of what had to be done in order to make the plutonium weapon. And this was then developed by experiments and tests done at Los Alamos. The actual thing to get the explosion started was a little sort of device at the heart of the plutonium weapon, which Piles and a man called Christie developed. So Piles was very central to the design of the plutonium weapon and its working, and Fuchs was very key also to that whole business. It was so difficult that one has to realize that much of this still was theory, and that's the reason why they tested the whole thing experimentally on the 16th of July in the New Mexico desert. The Trinity test, as it became known, was to see if in practice all of this theory worked, whether the plutonium would actually create an explosion or whether it would just sputter. And as we all know, of course, it made a very dramatic explosion. And that is actually to my mind, one of the most successful parts of the Oppenheimer movie. That I don't know how many newsreel films one has seen of an atomic bomb test where the bomb is, of course, exploded many miles away from where you're taking the movie, but you hear the sound of the explosion at the same instant that you see the bomb explode. Well, light travels pretty well instantaneously, whereas sound takes a while to get to you. And the Oppenheimer movie did this very dramatically because you see the tremendous flash and then the silence. And I imagined the scientists at that time suddenly realizing it does explode. And that is the moment when it's almost Promethean that you see for the first time the incredible power, the energy that has been locked inside these atoms ever since they were formed. And you have explosively released it. And you see what was like brighter than 1,000 suns, I think was the description of the flash. And nobody anticipated it would be that powerful. And they're all watching 10, 20 miles away, realizing that in 30 seconds to a minute, the blast wave is going to arrive. And that's the moment when I think if there was any panic, people were flat on the floor, facing away, covering their heads. And then this sonic boom passes. And as this sonic wave propagates outwards, it bounces back from the surrounding mountains. And I said in the book, like a form of sonic radar, you were mapping where the mountain chains were up to 50 miles away as the boom from the bomb reached them and bounced and came back in echoes. So it was a very dramatic occasion. And I think that was one of the things that the movie did very well, that you had this 30 seconds of tension, of silence, as you think, oh my God, what is going to happen next?
Yep, you're totally right. And I just watched that again recently after I finished the book, and it was like a solid 30 seconds of real time in the film as they're all reacting to the light show in front of them, essentially before the sound wave hits them. And it really is just astonishing and so well done. Just
I mean,
tremendous
ironically,
tension and
yeah.
release of tension.
Yes, I mean, I started the book with my description of all of this. And in the first draft, I should say I was writing the book 6 months at the end of 2023 when I was having successfully the good parts of nuclear physics used to help combat cancer, which successfully it did that. But I spent that 6 months writing
Hmm.
the book because I couldn't go out while all this treatment was happening. I couldn't even see the Oppenheimer movie. And in my first draft, I made the comment about how many times one had seen the bomb explode at the same you heard it explode at the same moment you saw it, even though it was 10 miles away. And then when I went to see the movie finally after I was okay again, and I discovered that they did it right, so I had to rewrite that bit in the thing to point out that Oppenheimer actually got it right.
Wow. Yeah, I really enjoyed it as well, and I was very eager to get your take on it because you would, of course, be much more familiar with this original source material than I was. But I certainly enjoyed watching it, and especially after reading the book, because it was so funny to me. I was reading through, and then the film cuts to like a Fermi's nuclear pile underneath the squash court. I'm like, oh,
Yes.
I just read about that, and it really is a gigantic pile of uranium and graphite, just like in the book. That's incredible. And then
Yes.
Teller
I mean,
sitting in the back of the room and being very difficult with everyone. Apparently, just like
yes.
you said in the book, he was hard to get along with, and it was really added a lot of necessary perspective to the film.
I mean, Fermi's 1942 the reactor under the squash court, that certainly is accurately portrayed. That is what the American side of it produced. The demonstration that is in practice, it is possible with enough uranium to liberate energy at a rate that could be useful for creating nuclear power. And that, in a way, is the moment when the atomic age, if you like, was sort of began. It was like fulfilled in the explosive version 3 years later. But Fermi's nuclear reactor was the first demonstration that in the real world you can indeed extract energy from a large amount of uranium and use it to produce power.
Yeah, just amazing things happening, and they happen so quickly too. Is what it felt like. Just a space of a few short years, like you said, there were so many tremendous advances. Tremendous and terrible, of course, in so many ways, but just an
Yes,
extraordinary period of history.
but I think also this shows how the nature of science has totally changed. Because when we started this chat, and I was talking about 1900 or so, and I said you had one person, maybe two people working together on a bench top with bits and pieces they could find around them. By the time we've got to the Manhattan Project, we've got a whole nation industrialized, working towards a common purpose. You've got leading scientists from all around the countries that are involved in the Allied war effort combining together to solve a problem which is almost impossible. And in the case of the plutonium weapon, had Piles and Fuchs and von Neumann not cracked it mathematically, it might indeed ended up of having been impossible. So it was a vast effort. It's in that sense that we see both the nature of science evolving into big teams, big apparatus, big scientific endeavours. That on the one hand, but also, as I said, had there not been the impetus of the war and the fear that if we don't get there first, we will get there last, and if we get there last, it's all over for us.
Right.
But for that, could you have imagined a whole nation being diverted to focus on this one particular project? In peacetime, I can't imagine that easily happening. So we might well, have seen nuclear physics as the source of reactors and so forth, and it might have had a different perception in people's minds.
Yeah, I agree, and it's unfortunate, in my opinion, that so much nuclear research has essentially some bad PR. I think, especially with people worried about nuclear reactors, located anywhere near them because they've heard of these few famous disasters and that sort of thing. But there's so many benefits and only a few drawbacks. But those drawbacks have unfortunately been very highly publicized.
Yes, I draw the analogy with what I call the air crash phenomenon. Nuclear accidents are very few and far between. In actual fact, the number of people killed in them has also been very, very small. But when they happen, they create a big news item. Just like when an air crash happens, it creates a big news item. Now, people really react to the air crash news, and they're still very happy to drive themselves to the airport, which is a much more dangerous activity.
Yep.
And it's a bit like that with nuclear power versus other forms of power. That conventional power stations are producing and spewing noxious stuff into the atmosphere. The number of people who have died through respiratory ailments or what have you, it is countless. Ironically, even green energy, windmills and solar farms, people have been killed by getting electrocuted or so forth. We're talking, handfuls of people, but we're still only talking handfuls of people in the nuclear accidents, which you can almost name on the finger of one hand. 3 Mile Island, Fukushima, Chernobyl, and in the UK, Sellafield, and that's it. And we're talking over 80 years. So it is remarkably safe. It's remarkably well understood. And the vision that people have is that, but could it somehow explode? And the answer is no. The route starting from nuclear fission, the fact that there's these two forms of uranium, 235, which is the explosive, and 238, which is more like a blanket. If you go the explosive route, that's a completely different direction than going the nuclear reactor power generation route. I was asked once, would you be happy to have a nuclear power station at the end of your garden? I said, well, as long as I couldn't see it. But I don't have a problem. I live about 7 miles away from what used to be a very big conventional power station. And were that converted to a nuclear power station, I'd be more than happy.
Mm-hmm. Yeah, I understand that there have been nuclear power plants shutting down all over Europe, and I don't know that we're even building any in the U.S. right now. We might be. I haven't checked, but it just seems like such a terribly missed opportunity for the world, really.
Yes, and I think understanding why the public is so concerned about it, as I say, it's hugely psychological. It's the same thing that we worry greatly about air crashes, even though that it's the safest form of travel that there is.
Yep, absolutely. So, Frank, I really enjoyed reading this book. It was a wonderful, eye-opening, experience for me, and it's something I strongly recommend for all of my listeners, anybody who is interested in the history of nuclear weapons, but also the history of science, because it's really amazing to see the methods that were applied, these ingenious and brand new methods that were applied throughout to advance knowledge. The book doesn't stop with the end of the Manhattan Project and the detonation of the bombs in 1945. Of course, it goes on from there into the development of hydrogen bombs and that sort of thing. I'm curious, though, what is it that you think it might be coming now? Like, what's on the horizon for nuclear physics development and research over the next few years? I mean, what can we expect to see coming up down the road?
Well, I suppose it depends what one refers to by nuclear physics. I mean, with regards to nuclear weapons and so on, sadly, even by 1961, when the Soviet Union exploded Tsar Bomber, which is the Russian for the king of bombs, which was 50 megatons. I think that's about 3,000 times more powerful than the atomic bombs that were exploded over Japan. That the original design, Khrushchev had wanted to make a demonstration of Soviet power. This was a time when you had the Cuban Missile Crisis. JF Kennedy was a relatively new president, and Khrushchev thought that Kennedy was weak, and so he wanted to make a demonstration with a 100 megaton weapon. Now, Andrei Sakharov, who was the lead scientist on the Soviet bomb project, calculated that 100 megatons would create so much lethal fallout that it would not only probably go around the atmosphere of the globe 3 times and fall out literally everywhere, but it would get into the food chain and probably contaminate and affect the DNA of people through the generations.
Oh my gosh.
And so, you were getting here into real madness. So Sakharov secretly managed to cut the strength of it in two, and did so in such a way that it became relatively clean, if there is a meaning to such a phrase. But that is the biggest weapon ever exploded in the atmosphere. And by this stage, Sakharov was beginning to proselytize that this is madness. I mean, the Tsar Bomber itself weighed 20 tons. Well, that was delivered by a specially designed aircraft. There was only a 50-50 chance that the plane would manage to escape the blast itself. So you're getting the stage of madness. You're not talking about something that could ever be used in warfare. It's just a demonstration of what you can do. And of course, atmospheric testing then stopped. So there's none of that anymore. Testing of nuclear weapons, in a sense, now is all done by computer codes, and it's still secreted. And that's something that I know nothing at all about any more than you, with maybe people listening to this program who know more about it than I do. So on that side of things, that's sort of clear. What is currently happening in Iran, that is a thing that is currently obviously of interest, that what the Iranians are actually doing. Again, I don't know. People in the intelligence area will know much more than I, though it is clear from what the atomic energy or specters found was that the Iranians had been enriching uranium up to what they said, like 60%. I said earlier that ordinary uranium is completely safe. That was Bohr's recognition of the paradox that the rocks around us aren't exploding. Mm-hmm. You've got to enrich. And enriching by about 1 or 2% is sufficient to start liberating energy in a ton of the stuff in a nuclear reactor. And so if you want to make nuclear energy for the use of society, you don't need to enrich very much at all. And that is what the Iranians supposedly were doing. So there's no reason at all why they need to enrich 20, 30, 40% to do that. To make a practical weapon, you need really to enrich up to nearer 90. So they are not near, or they were not near to making a practical weapon, but they were certainly far more than was necessary for what they supposedly claimed to be doing.
I see.
So that's my only take on that. The other thing, though, the fact that senior nuclear scientists were killed in one of these blasts, well, I don't think that's very significant at all. I mean, what I've been telling you about the atomic bomb has been known for 80 years. Making an atomic bomb is no longer require any secrecy, that everything you need to know in principle is out there. And your senior nuclear scientists being killed, well, okay, so the next people down in the chain, or even the graduate students, will be able to do that. A hydrogen bomb, a thermonuclear weapon, is a totally different business. That is still highly secret. And to work it all through requires very advanced scientific know-how. But even I mean, in my book, I've put together as much as I've been able to find in the open literature on what I, as a nuclear scientist, have been able to work out for myself. But the details of this I know nothing of. If it was a thermonuclear weapon you were talking about, then killing the few people who knew how to do it would have relevance. But that's not what we're talking about here at all. Okay. That's a totally different kettle of fish. The last thing, though, is, I mean, nuclear physics and nuclear science itself, the frontier has evolved out of nuclear physics and Ernest Rutherford trying to understand back in the 1930s what the atomic nucleus is. It was discovered to be made of protons and neutrons. We now know that the protons and neutrons are made of smaller seeds called quarks. It's like a cosmic onion. You keep going to deeper and deeper layers. And so we now know that the ultimate seeds are made of quarks. That there's no weaponry in here. There's no NASAs in here. There's absolute curiosity as to how is it that the stuff that you and I are all made of and that everything in the universe is made of came to be in the immediate aftermath of the Big Bang. And I would say the frontiers of the developments from nuclear physics today are the world of high-energy particle physics and the accelerator at CERN, which recreates in collisions between protons the sort of conditions in a very small volume for a very brief moment, the heat of the universe as it was about a trillionth of a second after the Big Bang. And by surrounding these little collision sites with very sophisticated detectors, we're able to simulate and investigate the nature of the laws of physics as they were the moment the universe came into being. And from that, beginning to fill in the picture of how from 13.8 billion years ago, we got to the state of things as they are today. So to me, the great irony here that the development of nuclear physics has led us intellectually to a profound understanding of the nature of almost creation itself and the way that the universe has developed. We've discovered this remarkable source of energy that has been trapped inside the nuclei of atoms ever since the Earth began. And if you like, that this almost, if there is a reason to our existence, it is we have found out this great secret. And if we don't have the imagination to be able to use that in a positive way, I find that as a failure of humanity.
Mm-hmm. Yeah, very well said. Yeah, absolutely. That's some big questions still being answered, still searching for the answers. That's amazing stuff, Frank. Yeah, a lot of food for thought there.
And I hope that somebody listening to this, a youngster, will actually put that to task and maybe solve the big questions and make some breakthroughs in that direction.
Wouldn't that be incredible? Absolutely. Well, yeah, thank you so much, Frank. This has been an amazing conversation. I really loved your book as well. Now that it's been published, are you working on yet another book, or are you moved on to a different project?
Well, at the moment, I'm preparing and giving many public talks and interviews like this and spreading the excitement.
Oh, okay.
And actually, from the questions that I get at the end of these talks, start developing thoughts in my own mind as to how to better explain some of the things that I have already tried to explain in the book, what people are really interested in. And from that will emerge the real question of, so what do you do next? And I am actually very interested in a man called John Ward, who you probably will never have heard of, but he claimed to be the father of the British hydrogen bomb and was never given credit for it. He wrote a letter in 1985 to the then Prime Minister of Britain, Margaret Thatcher, saying that I invented this thing, I was never given credit. I would like to have some credit now, please, which, of course, got immediately binned. But the thing was that this man Ward was a true genius. The word genius is thrown about very easily, but he had really made great insights back in the 1940s that became the foundations of much of modern physics, which is perhaps a reason why he was indeed called back. He was working at the Advanced Institute in Princeton. He was a Brit working there in the 1950s, was called back to Britain to solve the problem of the hydrogen bomb, because after the war, the Americans froze all of their allies out of nuclear know-how, perhaps because they were suspicious of the spies that had been discovered. At that stage, the American spies had not yet been revealed, but they had the impression that their allies were untrustworthy. And so Britain, in particular, had to go it alone and solve these problems itself. And this man Ward was called back to do it. He claimed that within 6 months he had solved the problem, but that for some reason the Brits wouldn't do it. And so he then just sort of quit and went back to the States, which created, I now know, quite a lot of worry in the powers that be here for security reasons and so forth. The second half of his life, from then on, he died in 2000 or so. He became totally paranoid, convinced that the security forces were watching him, that his phone was being tapped and so on. I think probably he was right. But it's a fascinating story that I'm just beginning to unearth, and I will hopefully tell you someday where it led.
Wonderful. That does sound very interesting. I love stories exactly like that, quite frankly. So that sounds great. I'll be watching for updates from you in that case.
Okay.
So
in the meantime, help destroyers of worlds, well, not destroy the world, but show that there's a great world out there that hopefully nuclear physics could lead us to.
Yeah, of course. There's a lot of positive inspiration in the book. It's not just a look at the cost of nuclear weapons. It is a very balanced take, I felt, because it was really inspiring to see so many of the great minds that worked on these projects that led off in a variety of directions, quite frankly. So it was really good to read.
Well, I'll just finish by saying, how it all happened was about 5 years ago. My then 10-year-old grandson suddenly asked me in a walk to town, "Grandpa, what do you know about Tsar Bomba?" Well, I'd never heard of Tsar Bomba. Then he started telling me all about this Russian weapon that had been exploded. It was the biggest ever, and so on. And I was astonished. I thought, what on earth do they teach them in schools nowadays? But then I went away and started researching it, and I became fascinated with this. How was it in just 70 years from finding a smudge on a piece of photographic paper, so small, as I said, that you almost missed it, they were able to solve the puzzle of what had caused it and develop from it a means of liberating nuclear energy in such a dramatic way that it could kill everything on the planet. And I thought, this is like a detective story. You're the detective in charge. You've got one clue. What do you do with it? And I then wrote the book about that.
Fantastic. That's a wonderful inspiration there. It all started with that innocent question from your grandson. That's terrific.
Yes.
Wow. Well, thank you so much, Frank. Do you have a website or social media handles or anything like that you'd like to share with the listeners if they want to follow along?
@CloseFrank, all one string, on X, or Twitter, as I still prefer to call it.
I'm always going to call it Twitter myself. I'll never be able to call it X, unfortunately.
Yeah, absolutely.
Okay, wonderful. Yeah, we'll put that in the show notes as well. Thank you so much, Frank. I'm definitely looking forward to your next book as well, and I really appreciate your time today.
Thank you.
Take care. If you're interested in more of Spycraft 101, look for my page on Instagram at Spycraft101. You can also find more great articles on my website, spycraft101.com. Thank you all for listening, and I hope you'll stick around because there's lots more to come.
Disclaimer. This podcast is for entertainment purposes only. The stories and statements expressed herein are experiences and opinions. They may not reflect the views of the host or the production studio. It's okay if you disagree with our content. No piece of media is right for everyone. If you love Spycraft 101, please check us out online, on Instagram, on YouTube, and especially on Patreon. Thank you for listening.